We had supersonic airplanes flying across our house every other hour. There was a speculation that we finished the end of science. If you understand fluid mechanics, you can understand society. My first Christmas evening, I was working in the lab. I did not regret it. A collection of people, in some sense, behaves like a collection of fluid particles.
Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour.
Welcome back to another episode of On Air Actually Rocket Science, a podcast facilitated by the Student Council of Aerospace and Geodesy. Today's guest is Professor Adams. You want to introduce yourself?
I thought the meeting is about introducing myself to you, so maybe we just go ahead with whatever questions you have. So.
Okay, so we're going to start every single time with little warm-up questions, are called this or that. It's essentially, we give you two options and you have to choose which one you like, and it's quick, so you don't have to really explain much, maybe if you want to, but it's just to start. So first question would be?
So Eulerian or Lagrangian approach?
What do you mean? I choose.
You choose between which one?
You can choose. You need both.
Oh, I mean, that works as well.
It's always like that.
Eddies or vortices?
Depends whether you are a turbulent scientist or a plain fluid mechanics student.
And what about you? What would you choose?
Both.
We see a pattern.
Supersonic or subsonic?
Yeah, both, of course.
It's going to be the first time everything is both. Next one is going to be funny as well. Turbulent or laminar?
Both. Because you cannot have one thing without the other. So.
Okay. Airplanes or helicopters?
Both. Because helicopters are more interesting in terms of aerodynamics, but planes can, reach higher speeds.
Okay. Cool. Navier-Stokes or Lattice-Boltzmann?
You keep me with saying both, because you cannot do research on Navier-Stokes without Lattice-Boltzmann, and vice versa.
Okay. Teaching or research?
Yeah, again, both, because I think it belongs together. So that's also why I think that teaching should be provided by the strong research professors, I believe. Right. The fundamental teaching, that's not shared by everyone, but that's my opinion. So research and teaching belongs together.
That's great.
Okay.
I think this is a good conclusion to this and that. We know that everything is important, guys.
I think this is the first time a professor answered both for every question.
Okay.
Maybe it depends on the questions, but okay.
Yeah.
So, I would like to start very fundamentally, because we do this where we make the podcast increasingly specific. So first a bit broad, and then we go. And first thing, obviously, we need to define what is fluid mechanics, and how would you explain to someone who has never heard about it, who's very unfamiliar with the concept?
It is the description of a collection of material elements who have no strict dependence on each other, or no strict spatial correlation to each other. So that's maybe the scientifically biased attempt to phrase it in one sentence. If you want to look at it from the other sense, I think it's the most interesting science in classical physics, because so many things happen. You see so many different phenomena. The description and the modeling of it explains so many other things. I mean, if you understand fluid mechanics, you can understand society, basically, because you think about how society behaves, and then you eventually say, okay, this is the same as a collection of people, in some sense behaves like a collection of fluid particles. So I think it's a very fundamental science which helps a lot in understanding of many other things.
That's a great answer.
Yes. Speaking of understanding, many people, when they come to the class, they get multiple explanations how an aircraft flies. So I wonder, how can you explain most accurately how an aircraft flies, and also what is the stupidest explanation you have ever heard how aircraft flies?
How or why?
How an aircraft flies.
I mean, it flies because you have a pilot.
Okay,
Typically,
then why there
or
flies?
remote
So
control.
I'm speaking about the physics behind
why?
it.
Yeah. Okay. I have. Sorry, I should not tell names, but there is actually a very nice colleague of mine. You may know him as well because you hear classes from him. He said he thinks the stupidest explanation is that an aircraft flies because the airflow across the upper side of a wing flows faster than on the lower side. And on the other hand, I think this is the most accurate description. So his opinion was that fluid particles which separate in the beginning of the leading edge, they don't know about each other. And how should they know that they should meet at the same time at the end of the airfoil? But that's exactly what fluid mechanics explains, that they should arrive at the same time at the trailing edge. I mean, at least in incompressible flows, but let's keep it simple. So that's the most accurate explanation. It's Bernoulli stupid. Sorry.
It's also very simple, but it's actually, I think, a good explanation.
Okay, so let's focus on actually your work here. And we have looked at all your research topics at your chair, but which one are you actually involved in? And what is your favorite topic that you're involved in?
Yeah, okay. So if you check the a little bit of background on the chair, you know it's huge, which personally I don't like. I like to have it smaller groups and stuff like that. But this is a different story, and maybe we can talk about it later. But it just grew when I took it 20 years ago. So I structured the chair into several independently acting research group. Christian Breitsanter has a group, Christian Stemmer has a group, Xingye Yu has a group, Thomas Indinger has a group. And this gives me the freedom to focus on my own group, so to say. And over the history of my scientific career, I've developed a strong interest in numerical modeling because I can, of course, quote famous people. As always, you need to deliver a quote. And there's Richard Feynman who said, only what I can create, I understand, something like this, right? He wrote it actually, it's supposedly written on the last blackboard writing before he died. So it's supposed to be somewhere at Caltech preserved. I don't know. And I think this is very true. But how can you recreate reality? The most fundamental way is to come up with a mathematical model, and they are so complex that you cannot calculate anything by hand. You have to put it on a computer. So I think that's the most fundamental way to understand actually what happens. And this is my interest, and this has developed over years, and I think we are pretty good at it. There's indicators for it, of course, and most recently I have become interested in hybrid modeling using artificial intelligence support and even more quantum computing, because I think it opens a completely new paradigm. It changes everything. Quantum, not just because of sheer power, but it's a completely different thing to have a digital representation of your physical problem on a computer and a quantum representation. It's completely different, but it opens so many new perspectives, and this is currently my most intense research: quantum computing for CFD and hybrid of computational fluid dynamics and hybrid approaches, merging artificial intelligence with classical approaches.
It's actually quite interesting. So you only develop numerical methods to solve the mathematical equations, or are you also co-developing the mathematical equations?
That's a very good question, because I think that goes really to the core, that nowadays we are at a stage where the numerical modeling goes beyond pure equations. So at the early times, as you probably know yourself, you first develop independently a mathematical model, Navier-Stokes equation, God knows what, and then you try to solve it as accurately as possible by a numerical approximation, finite differences, whatever else. But these times have passed. So now we are working on algorithms which are so complicated that we cannot, or is the wrong word, on algorithms which have not an immediately formal mathematical description. And this algorithm becomes the numerical model of physics. So we went beyond equations, and talk about basically recipes, what we believe, what the underlying physics is, which you cannot just write in a single closed form on a page. It's more like really like a do loop, something with ifs and cons and stuff like that. So an algorithm, and this elevates you much beyond what can be written on a piece of paper. And this is, I think, the current.
Okay, and it is fed then experimental data, or how is it?
Not only. I mean, we are so much advanced in computational fluid dynamics that we are very certain that the numerical results are correct.
Okay.
I like to tell a story from our research that for a long time we were struggling, not being able to match data with for a supersonic rectangular nozzle with experiments, and then by looking even more closely at the numerical data, we actually showed the experimentalists that they had a leakage in their experiment, which they didn't know about, and we were reproducing the leakage, and then a little leakage, and then actually the numerical simulation validated the experiment. So I think we are at that state. So in some people may call it bootstrapping. So we generate our own numerical data by very high level, high quality simulations, very expensive, and from them we derive simplified or alternative models, hybrid or quantum.
But you have been having the chair for 20 years, you said. Has anything changed in that? Because I'm thinking computational, like parallel computing, is getting better ever more slightly, and then this must be like very exciting for your field in that sense. Because 20 years back, you maybe took for something half an hour. Now you can say minutes, seconds.
Yeah. I mean, when I was postdoc at Ames, there was no browser. Well, the first internet browsers just came up. The performance of the first computers was comparably terrible, but we had several paradigm shifts. When I was doing my PhD, we were working on vector computers. The fastest was like a Formula One machine. Very few people could afford them. Very few institutions could afford them, and you were very, proud that you were one of the few accessing this extremely expensive fast machines. But then there was, as you mentioned, the shift towards commodity CPUs, parallelization, which was a completely new paradigm. We had to rewrite basically our research codes, thinking them from the end, not from the beginning. And now it's artificial intelligence, which is another paradigm shift, and the next one will be quantum computing for sure.
Speaking of your PhD and also looking even more back to the past, you have done your postdoc at Stanford and the NASA Ames Center. What was your experience there, and what have you learned or researched there?
The experience was that this was kind of still the end of a golden time of research. There was lots of funding. There was no money restrictions. Not that I became rich, but I never had the feeling that I was limited by resources in a sense. So I enjoyed a lot of research freedom. I enjoyed the research spirit at Stanford a lot. It was, no bullshit stuff. You immediately dove into the subject. You had incredible people around. I remember one person, Bill Reynolds, who unfortunately died by cancer some time ago. An incredible person who understands things much faster than you yourself, and this becomes really like a beacon. You try to orient yourself, and it was incredibly motivating. I mean, I did not regret to work after I arrived there. My first Christmas evening, I was working in the lab. I did not regret it because it was so much fun. It was nice to be in the evening by yourself and trying to think, and so it was an incredibly motivating environment. It nowadays became different, to be honest.
Okay. Yeah, I mean, we wanted to, because you're already at your, let's say, past, we can maybe also delve into even further back. You studied at Stuttgart, and you also did your PhD later at TUM, right?
Well, it was one of these constructions where I did the research actually in Göttingen.
Okay.
But as my supervisor was not a professor, he became a professor at ETH then later on. I had an official supervisor in Munich.
Okay, I see. But then we wanted to also essentially, where did your love for fluid dynamics develop? Was it already while you were studying? Was it Okay. And how come? Was there an event where you sat in a lecture and you had an enlightenment, or was it like a more gradual process?
But if you think back about your own career in school and maybe later, once you finished once you graduated, you will probably see that some people had an influence on you, and sometimes maybe not the people whom you would like to go to drink a beer with, right? So I had a math teacher who was a little bit rigid. Maybe it was good for me at that time. So with him, I detected my interest in math. And then one thing came to the other. And I had a fluid mechanics professor who was actually not such a terribly good scientist, but I liked how he taught fluid mechanics, also more formal in a sense. And this maybe stimulated my interest in fluid mechanics. And so it was a gradual process. I mean, it's like you go into a funnel, right? When you finish your high school, you have all these great ideas coming out of your life, and everything looks like almost everything is possible. And then gradually you go into the funnel and you find your way, right? And gradually interest, as I mentioned, fluid mechanics is incredibly interesting. So I went into that, became more interested in the fundamentals and stuff like that. So it was a gradual thing.
Going one step even more back, why did you study aerospace? And for all the listeners who might finish high school right now, why should they study aerospace?
I cannot really give you a recommendation because I think situations are a little bit different now. So thinking back, I think when Neil Armstrong put his foot on the moon, I was 6 years old. We did not have. We had still a black and white TV with, I think, 3 programs on it. One didn't actually work too well, so it was very fuzzy. We had basically only 2 programs, and of course, the landing on the moon was a TV event. So for me, it left a very strong impression on myself. Other things too. I mean, that was the Cold War time. We had supersonic airplanes flying across our house every other hour. And I was watching them. They were just maybe 200 meters high. I don't know. You could see them. So I became very much interested in that. It was more like a feeling. And you start to dream because you do not have a mobile phone. You are not exposed to all these multimedia imprints. If you want to talk to friends, you have actually to take your bike and drive for half an hour to go and see them. It's not like FaceTime. And you have a lot of time to dream. I mean, if you are good enough in school, your homework is finished, and then you start to play and dream. And that's how it developed, that I had the impression, I want to be part of that somehow. And then there was several options, of course. Stuttgart was very highly reputed. They had a very restrictive numerus clausus at that time. And so I just tried, and it worked. And then, so.
And then later, because in that sense, aerospace was not always extremely research focused. It was a lot on application. It was a lot on doing things very much, getting things flying and getting things better and faster. But there was very little fundamental research, and it developed over time more and more, I would say. Or would you say how did that evolve in that sense? Because maybe you would have...
I think in particular for aerospace, it was clear that you cannot... at that time, you cannot make advancements without fundamental research. We were at the early times when, the aerospace still was struggling to redevelop after the war. Airbus didn't. I believe Airbus just started to exist when I was mid-80s, when I was starting my studies. So. There was lots of research interest also in supersonics, hypersonics, different from now. And you had the impression that aerospace research was much less utilitarian than it is now. It was much more driven by curiosity, find out new things, being able to simulate things. I mean, you could not compute the Navier-Stokes solutions around an airplane at the time. Computers didn't exist. We were the first student generation who had access to high-performance computers, which were ridiculous. I mean, I think they had memory of few megabytes. It's incredible. My predecessor generation, they put their programs on these cardboard things, right?
Yeah.
Stack of cardboards and terrible when you drop them, because then the code is broken. That was very much interest driven. Not so much, we need to make this fly. No, it's the other way around, right?
Yeah, that's what I see.
You know how an airplane flies, we just discussed it, and now you need to use it for your application. So perspective has changed.
But I mean, you're still doing, in that sense, fundamental research, even though everything is...
Yeah, but I don't know what it is good for, essentially. So there is, you just explore. And I think that's a very important part of university research, that a part of people should always do curiosity-driven research, and another part should be how to put it, like technology-driven, where you kind of know already the result. It's very important that you have both, because this is the most stimulating environment, I think.
Yeah. Some are horizontal, explore, some build on top of the other things.
Exactly.
It's actually very nice.
Yeah.
So, speaking of all your achievements here in 20 years of being the head of a chair of fluid dynamics, what was your biggest achievement here?
My most important achievement is the good students who I was happy to work with, doctoral students, and to graduate them. I think I was very fortunate to, in the average, have very good students, very good PhD doctoral students, and do with them very good research. And I think that's the biggest achievement on the long run.
Do you then see essentially science as a more, in that sense, the science for you, is it just like, I want to explore things, but also give to the world, in that sense? Because if you have, like, let's say your PhDs, you're essentially giving them your knowledge and expertise and your experience, and with that you shape the future of science. Do you feel like that's something that really excites you about science, or is it?
I think overall it's more important than actually your scientific achievements. I mean, to be honest, I will not never in my life come to a Nobel Award-winning achievement which changed the world. Of course, there is things which I believe are important and are breakthrough developments in terms of science. But I think the lasting effect is the many people. I don't know how many PhD students I graduated, but certainly high 2-digit numbers already. And this is they take your spirit and your ideas with them to the world. And I think that's a much longer lasting impact than maybe this great computer code or this new model which you develop. I mean, there are, of course, also certain things like that, but.
And how about teaching? Because I think that's kind of the earlier stage of giving your spirit to the students.
That's why I'm saying that I believe it's important that I consider myself as a good scientist, sorry, but that good scientists should deliver the fundamental classes. You may not like it always. I know from your response to the teaching reviews that you would like me to, be more slow, write more things down. But there's certain constraints always. We can discuss them, but we also can leave it. So, but I believe the way I teach, with all the restrictions and constraints, that it delivers a certain perspective on fluid mechanics. And again, the experience is that it doesn't address everyone, but it addresses the right ones. And my students, which I have right now, they are basically all homegrown, more or less. And so it is, as you said, it actually starts early.
What I wanted to ask is, were you always sure you wanted to go in academia? Or
No. I mean, as I said, it was kind of a funnel. Okay, I can maybe share something which doesn't need to be cut because I don't mention any names, but I did my diploma thesis at a local company in Karlsfeld, so you may be able to derive which one it is. And there I was working in the compressor design department, and I had the task of developing a graphics program to visual. I mean, it was early times. There was still these computers with the black screen and the green letters on it. There was no graphics, essentially. So they were not able to visualize their data. And so they said, okay, take a student and have him develop a a graphics program, very fundamental, rudimentary. So I did that, and I shared my office with a person. I hope he doesn't hear this now. Who was a kind of older engineer. And, he came in the morning, took his time, skinned an apple, and so forth. You know what I mean. And then I said, this is not where I see myself in the future. And that probably was part of the decision. Then when I finished my diploma thesis, that I looked for a research position. And that was the beginning of an academic career.
But can you see, because sometimes nowadays it's seen the other way, that companies are trying to really perform because there's so much competition and everything. And back in the days, research was very competitive. But now I feel like sometimes people take PhDs for 10 years and are essentially just living off the student status. Do you feel like you have seen this now, or is it more of is it not a real thing?
Well, I'm not in my environment. I think students. I mean, there are students who like teaching, PhD students who like teaching, and you know that most of them have also teaching assignments, and so some of them. I mean, you lose time if you teach. It's inevitable. So some of them it takes longer to graduate than other ones who don't have to teach so much. But my perception is that. That they actually looking forward also to finish research and go on. It's not like. I mean, there's of course permanent academic positions, and they have their specific tasks in teaching and also leading their own groups eventually. But I don't think that I observe right now doctoral students just hanging on.
Oh, that's good to hear.
No.
Also, when we researched about your chair, we noticed that it's really, really big. Multiple professors, a lot of PhD students. You said when you started that was different, right?
Yeah.
So why did it change? Because there was so many projects you wanted to do? Okay.
Not I wanted to do it. It to a large extent it grew by itself. So when I started, I took over the chair of Trockenbrot. His successor was Laschka. I don't know whether these names tell you anything, but Trockenbrot wrote some textbooks. He was a kind of famous figure. And it was an aerodynamics chair dealing about really aircraft aerodynamics. I think Laschka was before he joined from Messerschmitt Bölkow Blohm, I believe. So it was very applied research, and when I came here, it was not my piece of cake. So I started with fundamental research, and Christian Breitsamter was the lead scientist of Laschka at that time. And so the agreement with Christian was, okay, you continue this applied aerodynamics research, and I do my fundamental research, and we merge it together. And then there were other people, Thomas Indinger, Christian Stemmer, who also same story. I let them grow. Thomas Indinger, the automotive aerodynamics, Christian Stemmer, the hypersonics, and that enabled me to do my own stuff. And that is how it grew. We were just successful. And at that time, we filled demand here in the environment. So lots of industry wanted to cooperate with us. And that's how it grew. It was not that I designed it to be like that. It was just a demand. And if people come to you and ask you, can you help us? You say, yes, of course, if you have the capability to do it. And then so it grew a little bit out of my control, to be honest. It was too successful. And now we are in the process of breaking it down. You may have heard that we're trying to search now 3 tenure track professors to take over the fluid mechanics on the long run after my retirement. So we want to scale it down again to a manageable scale.
And I mean, you were saying that at some point you would want to retire, and between that and now, do you have anything which you feel like I want to get done before I end my research career, or is it just like I'll get done whatever will get done?
No. I last year, actually in 23, end of 23, I won my second ERC advanced grant. This is few things, formal things I'm proud of, because that's, I think, a very fair assessment of your research output. There's only very few people at TUM who received this twice, and that's what I'm doing now. So this is my current research, and this will last until 28, something like that. Brings me close to retirement, and so that's my highlight towards the end of my career. What happens afterwards, I don't know. I certainly don't see myself as one of the persons who, barely able to move, but still come to the office every day. I would like to maybe do something somewhere, China maybe, I don't know. Maybe not Beijing, but
as in traveling or
no. Yeah, both. I mean, not senseless traveling.
Okay.
Traveling with a purpose.
So I go to other research institutions and learn.
Yeah,
from them,
you earned a lot of experience, and maybe some people want to tap into this experience. The retirement money is okay, so if you can earn something on top, would be nice, and help other people. I don't know. Something like that, maybe.
Can we maybe break down one or two questions that you're currently dealing with to maybe give the audience a bit more specificity about what you're dealing with and why it's interesting, why it's relevant, and what is so cool about
it? You mean science-wise?
Yeah, exactly. On the grant that you, for example, got, what were, for example, the questions you proposed, so the thesis that you have, or the grant scheme?
Okay, so how to put it? If you, many processes in current, or let's be more concrete. So additive manufacturing is basically a process where which is physically very complicated. You expose a substance, in most cases metal, to very high initial energies, and you disrupt equilibrium, and then you hope that when this liquid metal melts, so it goes back gradually to equilibrium, something good comes out in the end. And this is very complicated because the flow of the metal melt determines the shape of the frozen metal, but it also and then the entire process also determines the microstructure property of the metal, the crystal shapes, and God knows what. And so based on that, we did some preliminary research on that in terms of simulations. Based on that, I had the idea that I want to generalize this aspect, that I look at a fluid or material which is at equilibrium, then it's exposed to a very fast, very intense energy input, for instance by a laser, and then it relaxes back to equilibrium. This all happens on very short time scales, laser exposure on nanoseconds, even shorter, and then the relaxation back to equilibrium happens on microseconds, also very fast, sometimes milliseconds. So I came up with the idea to look at this in a more general sense, relaxation back to equilibrium after disruption, and I wanted to merge my experience in numerical modeling of these processes before. In my first grant, we did basically preparation of that, and now open up towards hybrid models using, for instance, several concepts of artificial intelligence to come to generative realizations, which means you do not necessarily predict, you do not necessarily replace a numerical simulation. But as you know that the input and output data are all elements of a distribution, you want to generate outputs which sample the result distribution. That's what's called generative. So you generate samples from a result distribution, and that can be done by generative models, such that GPT is a generative pre-trained transformer. We use very similar architectures also to generate flow fields, basically. So that is basically what I try to bring together: the physical idea of fast relaxation towards equilibrium. I called it ultra-fast fluid dynamics because it has to sound catchy, and generative and prediction with hybrid methods. That's basically the research.
And so how would you, in that sense, if I need to think about it, how would you present it at the end? If you have your results, are you just going to have these sample data, and then you essentially take maybe an average over all of them and gain a better understanding of the whole thing? Or are you saying, I'm going to set up something which is so generalizable that people can really build on it? Or is it just going to be more of a...
The hope is that we, at least for a number of generic flow cases, we develop a data-driven tool which is able to generate reliable samples of the output of the process. So that's what I mentioned. So the ultra-fast fluid dynamics describes what happens between energy input and at the end what you maybe can use as a product, as a solution. I mean, there's even ways how you can use these things to transmit medication into the bloodstream and stuff like that. The idea is that we want to develop a tool which, at least for these few cases, are validated to show that they generate, without actually doing a simulation, a sample of the output which is representative of the reality of the real distribution. Basically, it's a little bit convoluted expression, but it's for me now. Maybe if you understood what I mean, it's good enough. I don't know.
Exactly. Actually, when you were talking about extremely hot fluids, I myself was wondering about extremely cold fluids. So, for example, I'm thinking about superfluids. I'm thinking of cryogenic helium, for example.
Yeah.
Have you ever thought about these things, or do you any ongoing research that you have done related to that?
No, but for a short time, actually, we did. I remember that at ETH, when I was doing my habilitation there, we were approached. I forgot who it was, but I think it was some people who were trying to make experiments for flows around submarines. And because submarines are very big, you know that the Reynolds number is extremely large for a submarine, and they came up with the idea to put it in a superfluid. I think it never worked, but that was my only connection I ever had towards that direction. So I was rather more interested in the hot end of the flows.
Makes sense.
Okay, I would say we focus now.
On hot, exactly. I thought we can transition to supersonic as we have
supersonic. Yeah, I mean, it's NASA, for example, is developing their next supersonic aircraft. What do you think about that? And maybe you know more about the
looking
project.
Forward to it. I hate flying for 14 hours to Hong Kong or something like that. I would be like to be there in 3 or 4 hours, of course.
Do you think supersonic flights can come back? Because, I mean, you lived in also know the times where it has been.
Yeah, but I never was able to afford it. So if it's, I mean, I'm really not the right person to ask. You should ask Mirko Hornung about this, whether it's economically feasible. If I can afford it, I certainly would use a supersonic plane. No matter whether the CO2 output is twice as large as with the subsonic, because it's just a hustle. This flying is just a hustle.
But have you seen the new demonstration from Boom Supersonic?
My son watched it because he was also looking forward to it. I actually didn't, because I kind of know what the target is, I think.
Okay.
So.
I see. Is your son also interested in aerospace in that sense, or?
More in the utilitarian sense. So he also likes to fly fast, if he can afford it.
Okay. Should we?
So I mean, I want to. What do you want to do?
Just one.
Okay, sure. We can go ahead with that. Yeah.
You can just.
No, I was even more a bit interested in still the research topic that you were doing a grant for, because I think this is something that people don't really hear a lot about. And where would you advise someone to start if they want to get, for example, into numerical methods for dynamics, everything? Is there somewhere, maybe you can do some promo for your courses at your chair now, maybe give the people something that they can get interested in?
I think just go there and try, because there's so many good open source and access codes. Don't try to look at the most complicated open form first. Take something simple, where at least the source code is short enough so that you get a rough idea what happens. and then play around. And of course, you need a certain background in fluid mechanics. You should not do that right in the first semester, maybe, but that's I think the most reasonable way to start. That you can detect how powerful these tools are. And then you can play around and see how you can manipulate them, what you can do with them. You can produce results, actually, which anyway are grossly wrong. And it's interesting because you can do non-physical things. And then maybe if you are then interested in it, and you get the hang on it, and then you will continue. If not, then do something else.
For people who want to focus more on aerodynamics or fluid mechanics, I mean, when you started, there was probably a lot still unknown, still to research. Would you say there's still something really groundbreaking that people could focus on, or is it more or less like small things that need to be researched on?
That is a good question. When I was doing my PhD, and when you were young and you start to philosophize, and there was a book, I forgot the author's name, sorry. The End of Science. It was very, very famous. Maybe you have heard about it. And there was a speculation that we finished with it. And then, of course, there was a counter movement which said, no, it's certainly not the end of science. And somehow this is my experience. It always goes on. You go. It goes somehow in cycles. Funny thing is that also research in fluid mechanics repeats. Many things I see right now in literature, I've seen it already 20 years ago or 30 years ago. But anyway, that's not what I mean. I mean, you fall into a trough and think, okay, everything has been done. And then something is detected which is new, and then you say, okay, no, it goes on. There is something new. Let's push in this direction. So, for instance, with new tools, hybrid artificial intelligence driven tools, you have many new opportunities to detect new things which you are simply not aware of. That's what I mean with one should not look on research from the end. I mean, of course, if you look from the end, you think, okay, we know how rockets work, we know how airplanes work. So the classical fluid mechanics, we know how it works. But that's not the way to look at it. You should just go ahead, try new instruments, new tools, and then you will find something new, I think.
All right. Maybe we can ask you as well how you're structuring your life around your research. Is it more that your primary goal is I get research done, or do you think it's something you like to do but you put focus on your health and on your family?
No.
Or so on your hobbies?
I struggle as everyone.
Okay.
So family is a big thing. I'm not gone into any details, but for my wife and myself, it was very clear that my wife and I share every responsibility at home. So my wife, for instance, last year worked in Vienna, so I was running the entire business at home. And that is without question. And I don't need to discuss. I don't need people telling me you need to be more diverse. You need to, be more open to other, because we do it anyway. It's just reasonable.
Yeah.
Why would I expect my wife to take more responsibility for cooking? I cook better than she does. It tastes better, so of course I do it anyway. So. That's you can. I don't put my profession above everything. Okay. I think it's always a struggle. Sometimes this is more important. Sometimes that is more important. Then your son has issues and permanent struggle.
Yeah,
there's no code book which tells you, okay, no, I do like this, do like this.
I can see that even when you get this much life experience, we all don't just one day have life figured out. That's one good thing. So maybe it would be a nice thing that although you haven't life figured out, but you probably have a lot of things that you have learned through your life that are probably very valuable for our listeners, or very valuable to other people. So if you had something to say to the audience, nothing before maybe the podcast ends, what would it be? What would you tell them?
I did not really come up with a catchy.
Doesn't have to be catchy.
It can just be from the heart. But as I said already, I think what Feynman said is good advice for if you are interested in research, and otherwise to boldly go where no one has gone before. I think that is the motto of life, because you face always new challenges, and every day has something new, and you have to solve it as best as you can.
Thank you guys for listening. We had Professor Adams on, and it was very interesting. So make sure to stay strapped for the next episode.
And also check out all our other videos. We produced a lot of podcasts already. So just check out our YouTube and see you